is 1 over 2 to the s theta of s. And so it's just going to be this line minus that line. So this guy goes, 4 goes, and so forth. We get 1 plus 1 over 3 to the s plus 1 over 5 to the s plus 1 over 7 to the s plus dot dot dot. And then we can, since we're talking about, we're supposing this is absolutely convergent, we can factor out the zeta of s. So we got zeta of s times 1 minus 1 over 2 to the s is equal to that guy. Now, you guys got it? Now we're going to treat this guy right here, we're going to treat him as one big guy, and we're going to multiply this guy by the next term, this next term right here, 1 over 3 to the s. We're going to multiply this guy by that, we'll get 1 over 3 to the s plus 1 over 6 to the s. Not even 6 because it's already been cancelled out actually by the 2's. The next guy would be 1 over 15, 3 times 5 to the s, plus, and so forth. We're just we're getting every multiple of 3 that hasn't been cancelled out by the multiples of 2. And then we're going to do the same thing. We're going to get this guy minus that guy. So you're going to, and factoring out because of absolute convergence, we're going to get zeta of s is 1 minus 1 over 3 to the s times 1 minus 1 over 2 to the s. And it's going to equal 1 plus the next guy that hasn't been cancelled out, 1 over 5 to the s plus just the guys that haven't been cancelled out.
So you're using that idea.
And so yeah, so does this ring a bell? Anybody remember what we've seen right here? Start. This is exactly what we're doing. We're going to continue this to infinity. Obviously, by induction, we're just going to keep going to infinity. So eventually, what we're going to have here, the next guy is 5 right here. He's the next guy that hasn't been cancelled out. So the next guy, we're multiplying this by 1 over 5 to the s. And then just subtracting this guy from that guy. And we're going to have all this times 1 minus 1 over 5 to the s minus 1 over 3 to the s, and so forth. And as you see from this picture, this is just a direct application of this algorithm. We're just going to have, eventually, we're going to just cancel out all the numbers to the right of 1, and we're just going to have, and here we're going to have all the prime numbers. So what it turns out being, so we have zeta of s times 1 over 1 minus 1 minus 1 over 2 to the s, 1 minus 1 over 3 to the s, 1 minus 1 over 5 to the s, dot dot dot, equal to 1. What's it called? Where all these guys range over, they're only the prime numbers. Everybody else has been taken care of in terms of multiples of these guys. And then we have 1, so we're just going to divide this side, the whole thing, by this, and we're going to get the familiar form of the Euler product formula. It's just the product over the primes of 1 minus p to the negative s to the negative 1. It's just a quicker way to write it. Exactly what you see on the corner down there. The negative, it's the same thing. So yeah, so this is the main connection between the zeta function and prime numbers. And look at what we have. We have a product ranging over the primes now. What's it called? So what would be the next logical step to do? So this, what I'm about to show you guys, has nothing to do with what Riemann did. He noticed this, but not exactly in this way. Let me get some drink. He noticed that what I'm about to show you guys is a more direct connection. Yeah, probably Riemann would have loved to have seen this, but because he wasn't able to get it in this exact same way. But either way, well, just to show you. So we have this product formula here. So what Riemann is, he defined this connection wherever this converges for s is defined as the zeta function. Remember how we were talking about this sum only converges if the real part of s is greater than 1? Well, now we're talking about this sum equal to this product, and wherever they converge, it doesn't matter, it could be greater than 1, less than 1, it could be anything. Wherever they converge, is the zeta function. Because we're interested in these prime numbers. Alright, so now we have zeta of s is equal to this product over the primes. It's called, what would be the next logical step? I mean, where we have this product ranging over the primes, we want to take it to the sum. So of course we're gonna take the log of zeta. Assuming this guy is absolutely convergent from before, we can always assume the real part of s greater than 1. He's absolutely convergent. Everything goes now. So yeah. So what is this going to turn it into? The exponent. Remember, you take the log of this guy. The exponent comes down. You can factor the -1 out of every single guy. So you just have the negative of the sum over the primes. See, now we're trying to simplify this. Now we have the sum over the primes of the logs of 1 minus e to the negative s, where the -1 up here has been factored out of every guy. And so yeah, it was this is what Riemann noticed. The logarithm of this guy gave us this, and look how beautifully, look how easily, I mean, we can rewrite this in terms of the prime counting function. We can do from n equals 2 to infinity of pi of n minus pi of n minus 1 log of 1 minus e to the negative s. These two guys will be, when n equals 2, pi of 2, pi of 2 is 1. Pi of, this is n minus 1, this is pi of 1 is 0. So this is 1 minus 0 times this guy. So you're counting, well, this is not a p now. This is 1 times this guy when n equals 2, which is exactly the first term of this guy. And so forth for 3. This little guy, I mean, it's almost obvious, this little guy is going to do what this guy is doing over the prime. Here how we just write it over the primes, we can just write it like this, put this guy in front of it, and we'll get the same sum.
Whenever n is not prime, that factor is 0.
Whenever n is not prime, this is going to be 0. It's going to be 0, so you're not counting that guy. What are we going to do? Keep simplifying. Negative n equals 2 infinity. Multiply this guy out. We're going to have pi of n log of 1 minus n to the negative s. Just remember, there's a negative sign in front of everybody. Minus pi of n minus 1 log of 1 minus n to the negative s. Alright, so we do this, and we can distribute the summation sign. We're going to distribute the summation sign, and then just rewrite the second sum in terms of pi of n. What we'll get is just negative of, and then we're going to distribute the summation sign, rewrite this guy to have pi of n instead of pi of n minus 1, and then recollect everything again. I can show you guys all the work right there, but it would probably, for sake of time, it's just, I'm just going to show you what you get. It's pretty elementary. You get pi of n times log 1 minus n to the negative s minus log 1 minus n plus 1 to the negative s. And so here now we have this pi of n factored out. And then this guy, this is where you start throwing calculus and analysis and everything. This guy can be written as a simple integral. This guy right here, actually the negative of this guy right here is nothing but this n, it's an n plus 1 of s over x to the s minus 1 dx. That's it. We evaluate this guy. I mean, I can do it if you guys want to see it. We just let u equal x to the s. This guy will simplify into n plus 1 over the s will cancel out, we'll get u minus 1. Yeah, u minus 1 du. You'll simplify to this. Then and then what's called this we know from calculus. This is just going to be n minus n plus 1. What's called 1 over u minus 1 minus 1 over u du. Integrating these two guys, log of u minus 1 minus log of u, evaluated n to n plus 1. This, though, remember, by the rules of logarithms, we're going to just bring this guy under, and we're going to have log of u minus 1 over u, which is just log of 1 minus 1 over u. And substituting back our original u equals x to the s, this is just x to the s right here. Putting in the bounds n plus 1, you get the limits. You get this guy, but the negative. You get log of 1 minus n plus 1 to the negative s minus 1 minus log of 1 minus s and negative s. Sorry for. That's why I actually wanted to bring this up for some.
You should have.
No. For the real seriousness, this is, I didn't even want to get into too much into this actually. For the other proofs, I'll put this thing up and write everything a little more presentable. But either way, it's just, you see how just using calculus, we turned that integral. We could write this guy in terms of an integral, in terms of the negative of this integral. So what it turns out happening, and this is where you guys are going to see what happened. So this guy is equal to the negative. Well, actually, so I told you, when we wrote it in terms of this integral, we get this guy minus that guy. So we can just bring that negative sign that was into the thing, switch these two guys around, get rid of this negative sign, and we just have n, the sum of n equals 2 to infinity, pi of n, times the integral from n plus 1 of s over x to the s minus 1 dx. And now we're summing all this from n equals 2 to infinity. Simple observation is that pi of n is less than or equal to n for every n, of course. So we're going to bring this guy inside right here. We're going to bring him in here, so it's just pi of n here. We're going to sum this guy through all the things, and we're from n equals 2 to infinity. So we're going to have the integral from 2 to 3, plus the integral from 3 to 4, plus the integral from 4 to 5, and so forth. At the end of the day, this is just the integral from 2 to infinity. So this guy simplifies beautifully like this. So he simplifies to the integral from 2 to infinity of pi of x times s over x to the s minus 1 dx. And this is equal to the log of zeta. And there you go. You have now, this is the guy we've been looking for the whole time. Pi of x, there he is. The guy who we just learned about in terms of the logarithm of the zeta function. So now, alright, so I told you Riemann didn't do it in exactly this way. Riemann probably would have loved to have seen this. I was pretty shocked. I was like, man, this is pretty cool stuff to have this direct connection. Riemann didn't exactly notice it this way, mostly because, really, from here we can't do much, because of this is too complicated almost, besides the pi of x. So this s has nothing to do with the x. You can factor out this s right here. But here it is. I just wanted to show you guys this this direct connection between the pi of x and the zeta function. This is, Riemann noticed something similar to this. He defined this function. He simplified things a lot actually by defining a j function. He called it